Hey guys, welcome to Rocky by Chem series. In this video, we will talk about thermal conductance or heat conductance. The two terms can be used interchangeably. In my previous video, I talked about the Fourier's equation of heat transfer rate. Now, the Fourier's equation is given as Q is equal to Ka dt over dx. You can also write it as Ka delta t over delta x. The delta t or dt are the same. There is no difference between these two. So this equation defines the heat transfer rate, and the K here is the thermal conductivity. The A is the cross-sectional area. The dt is the changes in temperature. The x is the thickness or the distance that the heat has to travel through. In this session, I'm going to introduce this term called conductance. Conductance simply means how good a material is in doing what? Transferring heat. How good, an inherent ability of a given material to do what? To transfer heat. That defines as conductance. Whereas resistance, that term called resistance means how poor a material is in doing what? In transferring heat. So this implies that conductance, C, and resistance are inversely related. Conductance is inversely proportional to resistance. Anytime a material has a good conductance, then it tends to have a very poor resistance. A material can never have good conductance and then good resistance at the same time. The two are rather inversely related. Okay, so as I said, conductance defines how good a material is in transferring heat. Now, before we can determine how good a material is in transferring heat, three things needs to be taken into consideration. Now, imagine that this is the material that I am going to test its conductance, or like a material that I'm going to determine whether it is going to have a good conductance or not. And I have a temperature at one side of the house. Let's say the inside of the room is having 25 degrees Celsius, and then the outside of the room is having, let's say, 4 degrees Celsius. Under normal circumstance, heat flows spontaneously from the region of higher temperature to the region of low temperature. This is what happens. And we know that conductance is the inherent property of the material to conduct heat through it. So there are three things that determines whether a material will have good conductance or not. The first one that we have to talk about is the thermal conductivity of the material. The thermal conductivity, K. Thermal conductivity is a constant, right? It is a constant. So some materials tend to have good thermal conductivity. A material with good thermal conductivity tend to have good conductance. And a material with very poor or low thermal conductivity tends to have a very low thermal conductance. So a very key factor of thermal conductivity is what is it's a very key factor that determines conductance of a given material is the thermal conductivity. This is constant. Thermal conductivity is constant regardless of the size of the material, regardless of the length of the material. Thermal conductivity always remains constant. So if, let's say, somebody uses an iron rod to conduct it, and then somebody is also using a very big iron like a very big iron slab or whatever, the thermal conductivity will remain the same since the two are made from the same material. Now, aside thermal conductivity, another key factor that determines the conductance of a given material is the cross-sectional area. Imagine that the flow of heat occurs like flow of water. Let's say the flow of heat is going to take place like the flow of water. And I have two pipes. This is the first pipe, pipe A, and this is my pipe B. Now, imagine that I have these two pipes made from the same material, and water is meant to flow through this pipe. Let's say water has to flow from this region to the other region in the same manner as this one. The flow of water will be easy in the bigger one because there is larger cross-sectional area. The cross-sectional area of the material B is very high or is very big. So more water will be able to flow through the bigger one compared to the one that is small. This also occurs in the, this is also similar to how heat flow occurs. If the cross-sectional area of the material is big, then more heat will be able to flow through it rapidly, and hence the conductance will be increasing. So conductance is highly proportional to the cross-sectional area of the material. Now, aside the cross-sectional area of the material, another determining factor of the conductance of a given material is the thickness of the material. The thickness X, right? The thickness X. Now, let's consider the scenario on top here. Imagine that I have another similar material that is of this thickness. Let's say it is similar to this one, just that this one is the one on top here, A, is very thick, but the B is what, thin. And the same heat is to flow through from this 25 degrees Celsius to the 4 degrees Celsius. You will realize that because this material is very thick, the distance from here to here is what, very high compared to the one from here to here. So the heat will be able to easily flow through the one that is thin compared to the one that is thick. So this implies that conductance is rather inversely proportional to the thickness X. The greater the conductance, the lower the thickness, and then the higher the thickness, the lower the conductance. So these three are the determining factors that determines the conductance of a given material. Now, let's combine every information here into a single equation. So when we have to combine everything into a single equation, we can say that conductance C is equal to K times A, which is what? Ka over the delta X. So this is the formula for conductance. This is simply the formula for conductance. And if you want to know resistance, resistance is simply the inverse of conductance. So resistance will be the inverse of everything here. So the denominator will come to top and the numerator will come down. So resistance is therefore giving us changes in the thickness, delta X over Ka. This is the formula for resistance. Good. Now that we know conductance C is giving us Ka over delta X. This is what we know. Let's try to fix this into the Fourier's equation. We know from the Fourier's equation that Q is equal to Ka dt over dx. So there is something common. Look at this. We have Ka here, and then we have dt. We also have Ka here, and then we have dt. So we can replace this whole thing with what? Our C, and then have Q to be equal to C delta T or C dt. You can write it as C dt or C delta T. It is the same thing. So we can rewrite the Fourier's equation like this, as Q is equal to C delta T. And if we are to make changes in temperature, the subject, you can get temperature change to be equal to Q over C. Or you can make either of them the subject. You can get C to be equal to Q over delta T. Either of them is correct. Yeah. So this is what I wanted you to know. We can also write the Fourier's equation as Q to be equal to C delta T. And we know how we came by this equation. This is because Ka over dt is the same as what? Conductance C. Okay. Now, as we are talking about thermal conductance, there are two subtopics that we will treat. The first topic is conductance in series. Conductance in series. And then we have conductance in parallel. In this video, we will treat conductance in series. And then in my next video, I will talk about conductance in parallel. So stay tuned for my next video that I will do after this video. Now, we're going to talk about conductance in series. Imagine that I live in a very cold environment. And because I live in a very cold environment, I built my house such that it will be able to reduce heat loss. It will be able to prevent heat from flowing through easily from the external environment, or like from my room to the external environment, to cause me lose temperature inside the house. So I used three materials to build my house. The first material is made up of brick. The second material that I used is made up of, let's say, concrete. And then the last material is made up of wood. So these are the three materials that I use to build my house. And I have my inside temperature to be, let's say, 25 degrees Celsius. And the temperature outside the house is around, let's say, -1 degree Celsius. So we know that under normal circumstances, heat will flow spontaneously in this direction from the room to the external environment because of the temperature difference between these 2 points. Now, the question is that these three stuff that I used to build a house are made from different components. This is brick, this is brick, this one is what, concrete, and then this one is wood. There are three different materials, and they will definitely have different thermal conductance. They will have different thermal conductivity and then thermal conductance. So let's take good note of that. Thermal conductance is dependent on the thermal conductivity. So because these are three different materials, we should expect that each of them will have different thermal conductivity and then thermal conductance. So we know that for the heat transfer rate will remain the same. Heat transfer rate will remain the same, but the conductance for each of the material is gonna change, right? Each of the materials will be having different conductance, and we have to calculate that. So if we want to know the conductance for the first material, let me call them A, B, C instead, to make things easier for us. A, B, C for the three materials that I used to build the house. So because they are made of three different materials, then they will have separate conductance. So we know that Q is equal to C delta T, right? C delta T. So this will be the formula for the heat transfer. But this is not what we are talking about. Right now, we are talking about the conductance. There are different materials. Material A is different from B, and then it is different from C. So each of the materials will have their separate conductance. So the conductance of A is given as, we know conductance is given as Ka over delta T. Oh, sorry, delta X, where the A is the cross-sectional area of the material, K is the thermal conductivity, delta X is the thickness of the material, right? That's the thickness of the material. And now, let's move on to the second material. The second material will have CB, that is the thermal conductance B, and that is given as Ka over delta X, the changes in X for the material B. So delta XB, that will be for the second one. And then that of the third one, CC, will be given as Ka over delta XC. Don't forget that the K will be different because they are different materials. The K represents the thermal conductivity of each of them. So they will be having different thermal conductivities. And when we fix everything in, then we will use it to calculate the thermal conductance. Now, let's talk about temperature changes. We know that this is the inside of the room, right? This is the inside of the room. So we have the temperature T1. The temperature T1 at the interface of the room is the T1. And then the temperature close to the outside of the house is the last one that we have. Let's call this T4. But look at here. Look at this part, right? When the heat flows through the first material, like let's say from the inside of the room to the interface of the first material and then the second material, we will have another temperature here, which is T2. And then from here to here, the interface of the second material and then the third material, we will have another temperature, which is T3. So we have four different temperatures. The first one is the one inside the room. The second one is between the first material and then the second material. Third one is between the second material and then the third material. And then the last temperature is the one outside the house. So there will be different temperatures. So this implies that although the heat transfer rate will remain constant because it is the same heat that is flowing through all the materials, but the temperature changes will occur. Like the temperature change will not be the same. Temperature changes will be different after the heat flows through each of the materials differently, right? After flowing through each of the materials. So this implies that the total changes in temperature, like delta T total, right? The total change in temperature, that is just the difference between the one inside and then the one outside. This is just different changes. Total change in temperature is the initial temperature. The one at the far end, which is the room, and then the one at the other far end, which is outside. So the changes in temperature total will be given as the total changes in temperature from here to here. From the inside of the room to the first material interface, then from the first material interface to the second material interface, from second material to third material interface as well. So we will have total changes in temperature to be equal to the first one. So we have one, let's say we have first changes in temperature here. We have another one here, right? And then we have the third one here, delta T3. There are three different changes in temperatures. So we will have this to be equal to delta T1 plus the second changes in temperature plus the last changes in temperature. This is what it will be. Now, we know from the reduced Fourier's equation that I stated earlier that we have Q to be equal to C delta T. Now let's make delta T the subject. When you make delta T the subject, you will get Q to be equal to, you get delta T to be equal to Q over C. It will be equal to Q over C, right? So let's fix Q over C into this equation. And then we will have our total changes in temperature to be equal to Q over C1. Don't forget that each of the materials will have different conductance, but the heat will remain the same. So Q over C1 plus Q over C2 plus Q over C3. So something is common. We can get delta T total. Don't forget that this is the total. To be equal to Q, we can factor Q out because Q is the same throughout. So Q can come out, and then we have 1 over C1 plus 1 over C2 plus 1 over C3. This is how it will be, right? This is how everything will be. But we know that 1 over C, let me clean everything here, right? Let me clean everything here and continue. We know that 1 over C, inverse of conductance gives us resistance. As I said earlier, anytime you do inverse of conductance, it gives you resistance. So we can get total changes in temperature to be equal to Q, multiplying resistance 1, then resistance 2, and then the last resistance, the resistance number 3. So let's make Q the subject. When we make Q, which is the heat transfer rate, the subject, we get Q to be equal to the total changes in temperature all over R1 plus R2 plus R3. And you can expand this and get Q to be equal to, we know that total changes in temperature is the one at the room and then the one outside. So it will be T4, or let's say T1 minus T4 all over R1 plus R2 plus R3. So this will be the equation that we will get. Anytime we ask you to calculate for heat transfer rate in series, this is the formula that you will use. Heat transfer rate in series is given as Q to be equal to T1 minus T4 all over R1 plus R2 plus R3, and then you are done. As simple as that. Good. Now let's consider a worked example to help us test our understanding of the concept that we have learned today. A cold storage room is constructed of an inner layer of 12.7 millimeters of pine, a middle layer of 101.6 millimeters of cork board, and an outer layer of 76.2 millimeters of concrete. The wall surface temperature is at 255.4 Kelvin inside the room and 297.1 Kelvin at the outside surface of the concrete. Calculate the heat loss in watts for 1 meter squared and the temperature at the interface between the wood and the cork board. Thermal conductivities of pine is giving us 0.151 watt per meter Kelvin, cork to be 0.0433 watt per meter Kelvin, and then concrete to be 0.762 watt per meter Kelvin. So we are given all these parameters and we are to use it to calculate the heat loss in watts. We are just to find Q. Now, let's use a diagram to represent this whole scenario to make things easy for us. So this is the house. It is made from, or the cold storage room is made from 3 different materials. This is the first material. The second material follows. And then the third material follows. These are the 3 materials used to build the house. Good. And also, we are given the thickness of each of the materials and then their respective thermal conductivities. So the thickness of the first material, let's call this A, B, and C. The first material has a thickness of 0. It was given, the thickness was given in millimeters. So we need to convert this to meters. We have to convert the millimeters to meters. So that will be 0.0127. 0.0127. So this will be the thickness of the material. And for the second one, we were given the thickness to be 101.6. So when we convert this one to meters, we will get 0.0127 1016. This will be the second one. And then the last one, we were given it to be 76.2. So it will be 0.0762. Please don't forget to convert everything from millimeters to meters. Always convert from millimeters to meters. If you are given the thickness in centimeters, don't forget to convert it to meters as well. That is how we do the calculation. We do everything in meters. So don't forget. Okay, we were also given the thermal conductivities. The Ka, thermal conductivity of the pine was given to be 0.151. That of the second material was given to be 0.0433. And then the last one was given to be 0.762. So these are the three thermal conductivities of the materials given to us. Now, the question is asking us to calculate the total heat loss, Q. We know Q to be equal to T1 minus T4 all over R1 plus R2 plus what? R3. And one more thing, we have the temperature, we were given the temperatures at the interface of the house, like the T1, the one at the inside of the house, to be 255 Kelvin, right? 255.4 Kelvin, don't forget. And then the one outside was given to be 297.1 Kelvin. This is the T4. But we don't know T3. This is T3. We don't know. This is T2. We don't know as well. So these are the two other temperatures that we don't know. But we know the one inside the room and then the one at the outside. Now, as I said, heat loss Q is given to be the T1, the one inside, minus the one outside, T4, all over the individual resistance of the materials. But we know that conductance C, conductance is given as what? Ka over what? The thickness, delta X. And we know that the inverse of conductance, we want to get resistance, right? We want to get resistance. So we know that resistance is just an inverse of conductance. So that will be R is equal to delta X over Ka. We know this, as I said earlier from the introduction of this video. Now, because now that we know formula for resistance, let's use this to calculate the resistance of material A, B, and then C, so that we will just fix this into the equation and then calculate for Q, right? Let's do that. So we will get our R1, the first resistance, to be delta X1, like, I mean, the first changes in distance, or like the first thickness, which is the 0.0127, right? All over the K, thermal conductivity of the first material, which is 0.151, times the thickness. The question gave us the thickness to be 1 meter square. So this is 1. And when we compute this, we're going to get 0.0841. We're going to get 0.0841 Kelvin per watt. This is what we will get for the first material. And then the second material will be the same as the thickness, which is 0.1016 all over thermal conductivity of it, which is 0.0433, multiplying the thickness, which is 1. And this one will give us 2.35. 2.35 Kelvin per watt. And then the last one, R3, will give us the thickness, which is 0.0762 over thermal conductivity of it, which is 0.763, multiplying what? The thickness, which is 1. And this one too will give us 0.1 Kelvin per watt. Good. Now we have everything that we need, right? We have everything that we need. We have our R1, we have R2, we have R3. And we just have to fix everything into this formula. We know T1, right? We know the first one. We know our T1 to be here. We know the T4 to be here. So we just fix in and then we are good to go. So we will get the heat loss Q to be equal to T1, which is 255.4 minus the second one, 297.1, all over the sum of the three resistances, which is 0.0841 plus 2.35 plus 0.1, right? This is what we will get. Now let's compute everything. When you compute everything, you get the heat loss Q to be equal to negative 16.48 watts. The negative sign just shows that we are losing heat, because at the end of the day, heat is being lost, right? We are just losing heat. Okay, so the next question is that we are to calculate the temperature at the interface between the wood and then the cork board. This is what we're looking for. The temperature at the interface between the wood. This is the wood and then this is the cork board. All right. So we know from this formula that Q is equal to the C delta T, or you can write this same equation as Q to be equal to delta T over R. This is because we know that C is just the inverse of R. Like C is just the inverse of R. So I just replace this C with what? 1 over R. Good. We know Q to be equal to negative 16.48. And the changes in temperature is the one that we are looking for, the one from the room, and then the one from the one at the interface between the wood and then the cork board. So that is the T1 here minus the T2. So this will give us T1 minus T2 all over the resistance 1, the resistance of the first material, resistance 1. So when we work out the resistance 1, we had it to be equal to 0.0841. So let's fix it in. And then we will get negative 16.48 to be equal to T1, which is, we know T1 to be 255.4. This minus T2 that we are looking for, all over the first resistance, which is 0.0841. So just make T2 the subject. You multiply this by 16.48. Don't forget the negative sign. Use it for the calculation. So you multiply and then you send it to this side, and then the T2 will come here. And then you have your T2 to be equal to 256.79 Kelvin. As simple as that. So try this question for me. Try this out. Calculate the heat loss at the interface between the cork and then the is it the concrete at the between the cork and the concrete, which is the T3. I want you to do that for me. So this is very simple. You know the Q, and then you just replace this one with what? T2 minus the one that you're looking for, T3, all over the second resistance, resistance number 2. So fix it into the equation and then calculate this for me. Then comment with your answer, and I will tell you whether you are right or you are wrong. I hope you enjoyed this video. Kindly subscribe to my channel if you've not done so, and stay tuned for my next video on heat transfer or heat conduction in parallel.